We'll do it once I've done the presentation. We'll hand those out. Okay. Do we need to press record? Is you recording? Okay. Hello, everyone. My name is Brandon. I'm presenting on the history of Hilbert's 10th problem. This is sort of the Hilbert's 10th problem. I'll just start with some details. So you should all be familiar with polynomials. I'll go around the room and sort of you guys can answer these questions. So which of the following polynomials has an integral solution? This number 1, does that have an integral solution? Yes. Yes. Okay, what are they? 1, 0, negative 1, 0, 0, 1, 0, negative 1.
And there's like infinite.
No, that's it for this one.
For real?
It's just a circle.
Oh, integral solution.
Integral solutions.
Oh,
Yeah, we're not worried about rationals or irrational numbers.
Yeah.
What about for this second one? Does it have any integral solutions?
No.
No, it doesn't. What about this one?
It's hard to tell.
In fact, it does have a solution. I think that's my paper. The integers with least magnitude which solve this are 1,766,319,050 and 226,153,980. That's the least integer solution, but it does have one. And then this we'll discuss in a second. So in algebra class, you should have learned about the rational root theorem. For a polynomial with integer coefficients or rational coefficients, you can determine plausible solutions to the polynomial by taking every rational number, p over q, where p divides a 0 and q divides a sub n. Yes. Consider this polynomial. We know we can find all integer solutions using the rational root theorem to determine 6 candidates, which we need to test. Plus minus 9, plus minus 3, and plus minus 1. The only solution, if you just plug it in, is 3. And so, yes, this does have an integer solution. The only integer solution is 3. And so the rational root theorem gives an algorithm to determine whether an arbitrary polynomial with integer coefficients and in one indeterminate, only one variable, has a solution. So all of these polynomials I've been talking about are Diophantine equations. A Diophantine equation is a polynomial with integer coefficients where we're only concerned with integer solutions. We can ignore any solution that's not integral. Here's sort of a slight generalization of the solution set to a Diophantine equation. So consider these polynomials with parameters a1, a2, and so on, and then variables x1, x2, and so on. For this first equation, for which values of a sub 1 is there a solution in x sub 1? For which values of a can you choose so that there is a solution to the polynomial? Yeah? Which values of a?
Negative, a1 over 2.
No, don't solve for a. Give me an integer for which this polynomial, if you plug into a, this polynomial has a solution.
0.
0?
1.
No, not 1. 2x plus 1 does not have an integer solution. So 0,
Negative 2.
negative 2, 2, negative 4, 4, negative 6, 6. And so you can choose any even value of a sub 1 for this polynomial to have a solution. Does that make sense? Okay, what about this one?
Every square.
Every perfect square, yeah. What about this one?
Every perfect square is
No.
no solution.
That's not correct. You can choose when you have Pythagorean triples, are integers which satisfy a squared plus b squared equals c squared. If you choose any value of a and b for the first two parts of the Pythagorean triple, then you'll get a solution in the third So the solution, the values of A1 and A2, which allow for a solution to this polynomial, are the first two pairs in any Pythagorean triple. And this last one is hard. You guys will probably just have to guess.
Well, no,
One?
One is one. No, one
Zero.
does not.
Zero.
Oh yeah, it does. Zero. Okay. The answer is anything that's not a perfect square, except for a few exceptions at the low end. Okay, so what I just introduced is called a Diophantine set. So if you have some polynomial with parameters a1 to ak and variables x1 to xn, the set of k tuples, which allow for a solution to the polynomial, are elements of what's called a Diophantine set. So for this first example, this polynomial defines the Diophantine set of even integers. This one, the Diophantine set of perfect squares, and so on. Does that make sense? So the Diophantine sets are parameters for which they parameterize the space of some subset of the polynomials for which there exists a solution to that polynomial. Okay. Describe the Diophantine set defined by this polynomial.
Zero. How about no?
It turns out that the only solutions to this polynomial are prime numbers, in case you can't tell. So these polynomials, so constructing Diophantine sets from polynomials gets very difficult very quick. Okay, now we're done with polynomials for the most part. So a decision problem is a yes or no question. An algorithm solves a decision problem if it can correctly give, if it can correctly give a yes or no answer to that problem. A decision problem is decidable if there exists an algorithm which correctly determines the answer to the question. And if there is no such algorithm, the problem is undecidable. So here's three sort of tasks. Given an integer is n odd. Can one of you give me an algorithm, try to describe an algorithm which determines whether an integer is odd? Yes? So you take n, you divide it by 2. If it's divisible by 2, if its remainder divided by 2 is 0, you know that it is not odd. So the answer is no. If its remainder is 1, then it is odd. So the answer is yes. So yes, that's an algorithm which determines determines the decision problem. What about for this one? The second, given a positive integer is n prime.
Run through all numbers from 0 until n and try to see if n divided by that number is.
Well, what about 1 and n?
Above 1.
Okay, yeah, so from 2 to n minus 1 inclusive, you can check all of those to determine, and if one of those numbers divides n, then n is going to be composite, otherwise it's prime. Yes, what about this last one?
Yes? Question mark?
Give me an algorithm which does this. Anyone?
It doesn't exist.
We just discussed this. You can use the rational root theorem. You take every factor of a0, every factor of the highest degree coefficient, and you find all of the rational numbers defined by those two integers and just test them all. And there's only going to be a finite number of them, so you can just brute force it. So yes, this is a decidable problem. Okay. A set of tuples of integers, tuples of integers. Everyone knows what I mean when I say tuple, correct? It's like a 3 tuple is a set of 3 integers. 4 tuples, a set, not set, like ordered, an ordered set of 4 integers. So a set of tuples of integers is computably enumerable if there exists an algorithm which lists those tuples. So for example, the set of even numbers is computably enumerable because I can just go through and list them all. 2, 4, 6, 8, 10, 12, and so on. Same with the prime numbers, same with odd numbers, perfect squares. Basically any set you guys will be able to think of is going to be computably enumerable. Okay. Actually, no, we do. Okay, so the set of perfect squares, how would you enumerate that?
1 squared, 2 squared, 3 squared, 4 squared.
So you just take every integer and square it. Okay, good. What about the set of integers which are not perfect squares?
Just
All
exclude
the
everything.
excluding.
So how would you do that? You might just take every number, every integer, check if it's a perfect square.
Or you can just take enumerate the set, and then just take the set of perfect squares and just delete them.
Well, the number of numbers is infinite. You can't create a set of infinite numbers. So if I ask for all the perfect squares under some upper bound, that would be a good strategy. But that's not the case. And a set of Pythagorean triples, yeah, just enumerate two numbers. So 0, 0, 1, 0, 0, 1, 1, 1, 1, 2, 2, 1, 2, 0, so on, so on. Okay, good. So all of those algorithms which enumerate something define computably enumerable sets. Okay, here's two important facts about computably enumerable sets. The first is that the decision problem of determining whether an arbitrary set is computably enumerable is undecidable. That means if I give you a computably enumerable set, there is no if I give you a set, there is no algorithm which determines whether it is computably enumerable. Does that make sense? Okay. The second one is that there exists a computably enumerable set with a non-computably enumerable complement. So a complement, think about even numbers. The complement of the even integers are the odd integers. The complement of the perfect squares are the not perfect squares. The complement of, there exists a computably enumerable set whose complement is not computably enumerable. The proof of that is out of the scope of this. Okay, so that's done with the hardcore math. So now we're on to the sort of more historical section. Okay. So David Hilbert was a famous mathematician born in 1862 and he died in 1943. He contributed to many diverse, basically every field of mathematics that was around when he was alive, and is widely regarded as the most influential mathematician of the late 19th and early 20th centuries. John David North, who's a historian of mathematics, wrote, David Hilbert's the greatest mathematician of his generation. There can scarcely be a mathematician who is not familiar with some aspect of his work. So yeah, he was very good at math. Here's some of the things named after David Hilbert.
Is that hotel over?
I'm sure you can find Hilbert Hotel in here somewhere.
Oh, there.
Second one. Yeah.
No, right up to the top.
Yeah.
Oh,
Right above.
oh, I see. Yeah, Hilbert space isn't here. There's many types of Hilbert space.
He worked on astronomy?
There's a lot of Schmidt too.
He did a lot of stuff. Like he was around for like 80 years, but like I think he was around for more than that. It's crazy. Okay. So in 1900, David Hilbert was invited to speak at the Second International Congress of Mathematics. This competition is held annually. It has been since 1899, and I'm sorry, it's held every 4 years. It's held every 4 years. So it was first held in 1896. Actually, I don't know when they started doing it every 4 years. The next one is in 2026, and it will be in Philadelphia. And so, at least you freshmen and sophomores, I feel like this was to organize a trip to that. That's like pretty important. Maybe you'll get the chance to go. Or not to the school, you can go on your own.
If you give an invitation there.
Maybe. So at this Second International Congress of Mathematics, Hilbert famously presented what's known as his 23 problems, which he believed would guide 20th century research. They were questions which he did not know the answer to, and which other people had tried to figure out and decided they were very hard problems. And solving them would not only give a solution, but sort of push the boundaries of mathematics, give new techniques, create new theories, and so on. Some well-known problems of those 23 are the continuum hypothesis, the Riemann hypothesis, and whether arithmetic is consistent, meaning whether it has contradictions or not. many of these problems still haven't been solved. The continuum hypothesis and consistent arithmetic have been solved, the Riemann hypothesis has not.
Well, the continuum hypothesis, it was proved to be unprovable.
It was proved that so the continuum hypothesis is concerned whether there exists a set with a cardinality, a size strictly between the size of the integers and the real numbers. It turns out that that statement it cannot be proved in the standard axiomatization of set theory. So these days, most people who are studying set theory or using set theory use something called Zermelo-Fraenkel set theory. I'm probably butchering that. Or Zermelo-Fraenkel set theory with the axiom of choice, in English called abbreviated ZFC. It turns out that the continuum hypothesis is not provable within that axiomatization, and that it's, whether you assume it's true or false, does not cause any contradictions. So it was solved. They now understand. You can assume it's true if you'd like. You can assume it's false if you'd like. But at least in Zermelo-Fraenkel set theory, it doesn't contradict anything. Okay, that's a little bit of a side. So Hilbert's 10th problem, as originally posed, said, given a Diophantine equation with any number of unknown quantities and with rational integer numerical coefficients, to devise a process according to which it can be determined in a finite number of operations whether the equation is solvable in rational integers. He was using sort of some antiquated terms here. Unknown quantities just means variables. Rational integral numerical coefficients just means integers. To devise a process according to which it can be determined in a finite number of operations whether the equation is solvable. Rational integers, once again, just integers, as opposed to like Gaussian integers, which is the integers and sort of the complex I, square root of -1. Note here that to devise a process according to which it can determine a finite number of operations, he's describing an algorithm. Hilbert's problem is one of two problems which were not understood mathematically when he stated them. This is not a process with a finite number of operations, is not a mathematically useful phrase. It doesn't have any mathematical content in it, and they didn't know how to define an algorithm for another 30 years. And so when he gave this problem, it was sort of ill-defined. They didn't have everything they needed to do to really ask it mathematically. So in the 1930s, because of the work of these four and other mathematicians, they sort of became able to give explicitly what an algorithm was. So Alan Turing, Alonzo Church, Stephen Kleene, and Kurt Gödel. Kurt Gödel and Alonzo Church are buried in the Princeton Cemetery. Yeah. If anyone watched Oppenheimer, the recent movie, Albert Einstein was in 2 scenes, I think, shown walking with Kurt Gödel. They both had it up at the Institute for Advanced Studies. Okay. So, because of the summary of all of their work on the foundations of computability is sort of summarized by Alan Turing in this sentence. It's that no computational procedure, or algorithm, will be considered as computational procedure here refers to what you can do as a human. It's a more qualitative statement. As an algorithm, unless it can be represented as a Turing machine. So essentially all this states is that a Turing machine, which was his model of an algorithm, his mathematical model of an algorithm, describes accurately, according to, this is a statement in philosophy, not mathematics. He believes it describes accurately what you are capable of doing as a person. A little later, due to the work of Church and Turing, they created the Church-Turing thesis, which similarly states that every model of computation, so any way you describe an algorithm, or describe a machine that can perform algorithms, is at most as powerful as a Turing machine. And so in this sense, a Turing machine is the correct model, a correct model of computation. This includes like quantum computers, for example. A common misconception is that quantum computers are more capable than computers, and in a sense they are. There's a lot of algorithms they can perform faster, but there's nothing that can be performed on a quantum computer that can't be performed on a classical computer. And that's agrees with the church Turing thesis. I've been sort of, like the technicalities of a Turing machine are sort of out of the scope of this presentation, but you all have an intuition for what an algorithm is, as we showed a few slides ago. Intuition is generally correct. So in the language of computability theory, Hilbert's 10th problem asks, given a Diophantine equation, any number of indeterminates, to devise a computable function which returns 1 when the equation has a solution and 0 when it does not, or show that the problem is undecidable. It's another important thing. Hilbert didn't realize that it was possible for Hilbert's 10th problem not to have a solution. He was a formalist, meaning he believed that mathematics was sort of an exercise in pushing tables around. And only after the work of Kurt Gödel did they realize that these types of questions could not have a solution. So in 1944, Emil Post famously said that Hilbert's 10th problem begs for an unsolvability proof. That brings us to some of the people who were important in the solution to Hilbert's 10th problem. So the first person is Martin Davis. He was born March 8th, 1928. I forget where he was born, but he grew up in the Bronx to two Jewish Polish parents. He went to Bronx Technical High School, or there's a famous high school. Bronx.
Bronx School of Science or something like that. I think it's science.
Something like that. He went to one of those famous magnet schools. He went to City College for undergrad, and then he went to Princeton where he studied for his PhD under Alonzo Church, who we just talked about. He became a professor at NYU and helped set up their CS department. He was a mathematician and a logician, and he helped start the field of computational complexity theory. At NYU, he helped set up their computer science department. And then in 1998, he retired from NYU and became a visiting, a few years later, he wrote a book and then became a visiting professor at Berkeley. Okay, and he died January 1st, 2023. So in 1949, Martin Davis proved that every recursive, or I should say computably, these are the same thing. Recursively enumerable and computably enumerable are the same thing. Every computably enumerable set is of this form. You don't need to know what that means. Essentially, all it means is that he now has a way to explicitly describe every computably enumerable set. That's why it's called a normal form, because it's sort of, it normalizes the ways in which you can express these sets. And he used this to construct a Diophantine equation with a non-Diophantine complement. Remember that the recursively or computably enumerable sets, exists those sets which don't have a complement. That's sort of a similar, there's some similarity there, and that's sort of a hint towards what's to come. The next important person is Julia Robinson. She was born December 8th, 1919. She received her PhD from Berkeley in 1948 under Alfred Tarski, who's another sort of well-known mathematician. She was hired as a professor at Berkeley after they learned she was nominated to the National Academy of Science. Initially she wasn't allowed to be a professor because her husband was also a professor in the math department, and they had a rule against having husbands and wives in the same department. And then she was elected as the first female president of the National Academy of Science, but she died of leukemia the third year of her term, so she couldn't complete it. In 1950, Julia Robinson conjectured what's called the JR hypothesis, which states that there's a Diophantine set D of two tuples of pairs of integers A and B, which satisfy some property resembling that they sort of exhibit exponential growth. She didn't prove this, she conjectured this. She was studying Diophantine sets, and this is something she believed to be true. Here we have a picture of Martin Davis and Julia Robinson next to someone else important who's to come. So in 1950, Martin Davis and Julia Robinson, who were unaware of each other's work, met at the 50th International Congress of Mathematics. In a book by Martin Davis, he writes, "It has been said that I told her that I doubted that her approach would get very far, and surely one of the more foolish statements I've made in my life." So Julia Robinson and Martin Davis worked closely together towards the solution to Hilbert's temp problem. The the third out of 4 important characters is Hilary Putnam. He was a famous sort of philosopher of science, and who also contributed to mathematical logic and computability. He was born in 1926. He was one of the leading philosophers. He was born in Chicago, Illinois. I forgot to mention. He received his PhD in philosophy from UCLA. He transferred. He started his PhD somewhere else. Maybe UPenn? He started at UPenn and then transferred to UCLA. And he got his PhD in 1951. He was radically political till the 1970s. He was always sort of involved in protests and that type of thing. And he became a professor of mathematics, or that's philosophy, not math. I think mathematical philosophy. That might have been a typo, I'm not sure. At Harvard until 1966. So Hilary Putnam and Martin Davis met in the summer of 1957, and they became close friends. They traveled together and would work on Hilbert's tenth problem. In 1959, Hilary Putnam, Martin Davis, and Julia Robinson proved that the JR hypothesis, if it is true, which they still didn't know, would imply that every computably enumerable set is the same as every Diophantine set, and vice versa. Remember, I gave a theorem before that said there is no algorithm that can determine whether a computably enumerable set, whether an arbitrary set is computably enumerable. If the notion of computably enumerable sets and Diophantine sets coincide, that would imply that there exists no algorithm which can determine whether an arbitrary set is Diophantine, and therefore whether an arbitrary Diophantine polynomial has a solution. But they still hadn't showed this. It was reliant on a conjecture by Julia Robinson. So in the biography of it was a biography by Julia Robinson's sister, but written as if it was an autobiography. So in this biography, Julia Robinson was quoted saying, "It was the custom in our family to have a get-together for each family member's birthday. When it came time for me to blow out the candles on my cake, I always wished, year after year, that the 10th problem would be solved. Not that I would solve it, but just that it would be solved. I felt that I couldn't bear to die without knowing the answer." Around this time, between the late 1950s and into the 1960s, all 3 of the people we've talked about so far were also trying to prove the opposite, that Hilbert's tenth problem was decidable. They had their doubts about their progress. I've been giving evidence that Hilbert's tenth problem is undecidable, which it is, but they did not know that yet, and so they were still trying to prove the opposite as well. So the last important person is Yuri Matyasevich. He was born March 2nd, 1947. He's still alive. He was born in then Leningrad, now St. Petersburg. He won the gold medal at the 1964 IMO for Russia, or the Soviet Union. He became a professor. For his PhD thesis, he worked on Hilbert's tenth problem, and he soon became a professor at the St. Petersburg Department of Steklov Mathematical Institute of the Russian Academy of Science. I didn't forget any words. That's the full name, and it's abbreviated POMI, P-O-M-I. So in 1970. In 1970, Yuri Matyasevich showed that the following set exhibits near exponential growth, and so proved the Julia Robinson hypothesis. These results were published in '71, and because they already showed the Julia Robinson hypothesis implied that Hilbert's tenth problem was unsolvable, he showed that Hilbert's tenth problem was unsolvable. In particular, he proved what's now called the MDRP theorem. M is Martin, is Matyasevich, D is Davis, R is Robinson, P is Putnam, therefore last names. That states that every computably enumerable set is Diophantine and vice versa, and as a corollary, Hilbert's tenth problem is unsolvable. Right after Julia Robinson learned of Matyasevich's discovery, She wrote to him in a letter saying, "Now I know it is true, it is beautiful, and it is wonderful. If you really are 22, I am especially pleased to think that when I first made the conjecture, you were a baby and I just had to wait for you to grow up." Yes. Okay, that's the end of the history of Hilbert's 10th problem. Now I need to tell you about what I did for my research project.
That was just the background.
So, Hilbert's 10th problem has been solved over the integers, but they don't know whether there exists an algorithm which can determine whether an arbitrary polynomial of other rings, which are sort of other algebraic structures, has a solution. So, for example, if I take any polynomial with solutions in the complex numbers, I know every polynomial with complex numbers has a solution. If I take over the real numbers, you can factor them. You can factor these polynomials and determine whether there's a solution. And so, there's these other rings, such as the rational numbers. People still don't know whether there exists an algorithm which determines whether you can determine a solution in the rational numbers. Yes. And there's all these other rings. Of particular interest to to sort of algebraic number theorists are whether Hilbert's 10th problem is solvable, the generalized Hilbert's 10th problem is solvable over number fields, which are finite extensions of the rationals and the irrational numbers. Many of these have been solved. Yeah. Okay. And some are still open. Okay. So here is a picture of sort of a meeting to discuss generalizations of Hilbert's 10th problem that took place in 2005. You can see Martin Davis, and then some other important figures. More recently, there's Yuri Matyasevich. This guy's name is Bjorn Poonen, Alexandra something, and this is Kirsten Eisentrager, who's a professor at Penn State. One important tool in proving or making progress towards generalization of Hilbert's 10th problem is elliptic curves. An elliptic curve is a type of, sort of a cubic polynomial with sort of an underlying algebraic structure. That algebraic structure is sort of described here, but it's not. The technicalities aren't important. And so for my research project, I am writing a summary, a sort of review article of how these curves are used towards generalization of Hilbert's 10th problem. Okay, that's it. So I'd like to thank Dr. Sood, Mr. Kemp, Kirsten Eisentrager, and my mentor Peter Rock for sort of helping me. We have Lindt chocolates, and they're not really apple pies, but they've got like apple pie filling. I'm not quite sure if my mom found the recipe before she decided to use leftovers or the other way around, but they taste pretty good.
Well done, Brad.
Feel free to take the apple pie as I promised.
Yeah, push the session in 5.
Don't eat the dark chocolate Lintz.
Which one?